All right, let's jump right in. Welcome to this explainer on construction and project management essentials. Today, we're taking a highly authoritative, completely fluff-free deep dive into the technical science, the strict codes, and the exact math that actually drives real-world construction. Listen, whether you're studying for the Florida GC project management exam or you just really want to understand how complex structures safely come out of the ground, this is for you. We're talking hard facts, structural laws, and absolute site safety. Let's get to it.
Here's our game plan for today's masterclass. We're going to follow a project's natural progression, starting with site layout and elevations, moving on to soils and earthwork, then diving into concrete, rebar, and formwork, before capping it all off with OSHA safety standards.
So let's kick things off below ground with Phase 1, site layout and elevations.
Before a single shovel even scratches the dirt, we have to establish the fundamental lines and fixed reference points that are going to dictate the entire geometry of the project. And for that, we need a benchmark. By definition, your benchmark is the absolute starting point. It's a fixed reference used to establish literally everything: finished floor, drainage, and grading elevations. Now, why does this matter so much? Because if you get your benchmark wrong, you definitively throw off every single subsequent elevation on the entire project. If your anchor point is bad, everything you build on top of it is wrong. Simple as that.
Now here's a massive trap a lot of project managers fall into out in the field: confusing setbacks with easements. They are not the same thing. A setback is just the required distance from a property line or a street to your structure. But an easement? That's a legal right for utilities, drainage, or access to cross the land. You might own the physical space, sure, but building inside an easement is strictly prohibited unless you have special approval. You really don't want invisible utility lines derailing your entire build.
Which brings us to FEMA and base flood elevations. In places like Florida, where you've got high water tables and serious flood zones, the lowest finished floor must sit at or above the required base flood elevation according to the building code. Getting this wrong isn't just some minor administrative headache. Improper elevations practically guarantee flooding, a complete denial of insurance, and failed inspections. It's a catastrophic, completely uninsurable mistake.
Moving right along, let's hit Phase 2, soils and earthwork.
Okay, so we've mapped out the site, and now it's time to move the dirt. Earthwork isn't just arbitrary digging. It's a strict material science. You really need to pay attention to the critical distinction here between bank cubic yards, or BCY, and loose cubic yards, LCY. BCY is the undisturbed volume of soil, perfectly packed, sitting right there in the ground. But the very second you dig it up, it expands, it swells, kind of like a sponge soaking up air. That fluffed, expanded soil is your LCY. And you must always use LCY to calculate your hauling fleets, because trucks haul fluffed soil, not perfectly compacted ground soil.
So let's walk through the exact mandatory soil swell formula that project managers use. Step 1, measure your bank cubic yards. Let's just say we have 500 BCY. Step 2, multiply that by 1 plus your swell factor percentage. So if we're dealing with a 30% swell, we multiply 500 by 1.30, which gives us exactly 650 loose cubic yards. Finally, step 3, divide by your truck capacity. If you're running 10 cubic yard trucks, 650 divided by 10 means you need exactly 65 loads. If you miss this math, your logistics and your budget are entirely ruined.
Once all that dirt is moved, it has to be stabilized. Enter the Proctor test. This is an absolutely vital lab test that establishes a soil's optimum moisture content and its maximum dry density. When you're compacting in the field, it has to match this lab-tested Proctor maximum. And I gotta warn you, if the soil on your site is too wet or if it's too dry, mechanical densification is simply going to fail. Hitting that optimum moisture is the absolute key to structural stability below ground. All right, the ground is prepped. Let's get into Phase 3, concrete, rebar, and formwork.
We are finally ready to pour the foundation. But this is governed by strict chemical mix rules, precise testing parameters, and massive structural loads. And that brings us to the slump test. Listen to me, this is a major exam trap and it's a huge field trap. A slump test measures the consistency and the workability of a concrete mixture. Clarify this in your head right now. It measures workability. It does not measure strength directly. In fact, a higher slump usually just means there's more water in the mix, and that practically guarantees lower structural strength. You can never confuse an easy pour with final structural strength.
There are also a few non-negotiable concrete mandates you absolutely have to memorize. First, aggregates actually make up a whopping 60 to 75% of your total concrete volume.
Second, if your rebar is going to be permanently exposed to earth, you are legally required to have a strict 3-inch concrete cover. Third, the structural bond relies entirely on the rebar's deformations, those little ribs on the steel. And finally, never forget that wet concrete is a massive live load. If your forms are improperly braced, the lateral pressure from that wet concrete will cause deadly blowouts and collapses. When you're looking at mixing and delivery metrics, pay special attention to entrained air. Adding entrained air into concrete mixtures actually results in improved resistance to freezing and thawing. It protects the microscopic structure of the concrete against those harsh temperature shifts, all without compromising the fundamental integrity of the mix. You also really have to keep your cement type straight to prevent structural failures. Portland cement, that's your primary hydraulic cement for heavy structural concrete. Masonry cement, on the other hand, is a blend specifically used for mortar and stucco, meaning it is entirely non-structural. And finally, grout. As a project manager, you only use grout to structurally reinforce masonry cells and cavities. Do not mix these materials up. Their applications are strictly and specifically defined by code. We're in the home stretch. Phase 4, OSHA safety standards. We are wrapping up this construction cycle with the absolute non-negotiable laws of site safety. And we're going to focus specifically on excavation hazards because trench collapses are sudden and they are deadly. OSHA's trenching rules escalate strictly by depth. At 2 feet deep, spoil piles have to be kept back from the edge. At 4 feet deep, workers cannot travel more than 25 feet laterally to reach a ladder. At 5 feet, safety systems like shoring are legally required. And if you hit 20 feet deep, you legally must have a protective system that is designed by a registered professional engineer. To help you lock these codes in, let me introduce you to the 6534 memory trick. This is a great tool that represents the 4 most critical, highly regulated measurement numbers across all OSHA construction codes. Let's break them down right now. We start with the number 6. 6 feet is the exact height at which fall protection becomes legally required on a construction site. According to Subpart M, if you are 6 feet above a lower level in construction, you must, no exceptions, have fall protection. Next up is 5. Moving to 5 feet reinforces that absolute rule for earthwork we just talked about. Any trench or excavation that hits 5 feet in depth instantly requires protective systems. Again, no exceptions unless you are digging into entirely solid, completely stable rock. Continuing with our trick, we've got the number 3. 3 represents the precise number of feet a ladder must extend above a landing surface. If one of your workers is using a ladder to access an upper roof, those side rails absolutely have to protrude at least 3 feet past the edge for a safe dismount. And we finish it out with the number 4. Why 4? Well, because this contrasts the construction standard with general industry standards. While construction requires fall protection at 6 feet, general industry standards require fall protection at 4 feet. Don't confuse the two on an exam, and certainly don't confuse them in the field. General industry operates on a much stricter 4-foot fall rule. So as we wrap up this explainer, I want to leave you with a provocative challenge. Will a misread benchmark, a failed Proctor test, or a miscalculated water cement ratio be the variable that compromises your next structural build? Because out in the field, these aren't just exam questions or textbook theories. These precise metrics separate successful, safe projects from catastrophic, life-threatening failures. Respect the math, respect the code, and keep building it right. Thanks for joining me on this deep dive.